Good morning, my name is Pishraya. I'm from AC Department B section, and my tech talk topic is the oscillation and ringing finding worst case capacitive load. Introduction. It's a universal problem how to design an analog block when you don't know exactly what the capacitor load is going to be. It is disconcerting how often this problem comes up. In the old days, there was always the threat that the customer would hang something advised on your output pin. And today's system on chip SoC environment shelters most functional blocks from the application board, but you could still be blindsided by the wiring capacitance on the chip itself. Basically, you won't know how much capacitance will be clinging to your creation until the layout is nearly finished, and it could be changed at any minute. Even if you survive the layout, the real minefield is this: the blocks get reused, borrowed cells from the often blindly pressed into service without the original designer's knowledge or approval. Ironically, simple blocks or blocks with some unglamorous function are most likely to cause problem. Such modest blocks inspire complacency and as for more likely to be reused and less likely to be re-engineered for their new application. So a perfectly good design could come back to haunt you when it appears in an environment you never anticipated. Note, you know that the circuit can be stable with both light and heavy loads and yet ring like a bell when loaded with some intermediate value capacitor. Why do capacitor loads tend to make output ring in the first place? Certainly, wiring or the under inductance could be the culprit, but for active circuitry, feedback is usually to blame. That may not surprise you, but what is different here is that we will attack the stability issue without dissecting this loop. As an example, consider this simple. The analyzed circuit block in the figure 1, the amplifier inside the block is just frequency independent voltage gain with ideal single pole roll off. Without any external load, the load shown in the stable with the 90 degrees of phase margin. Note that the none of these features are required for the technique to work. This is just an example. The output resistance R out is shown in the figure 1 because it is critical to this discussion. At low frequencies, the loop gain of the feedback hides most of the resistance from outside the wall, and the effective output impedance of the block is only 1 ampere. Sorry, ohms. However, the things are not so rosy at all the frequencies. And like all the amplifiers, the one inside our example block has limited bandwidth, so the output impedance is not going to be 1 ohm everywhere. Above 10 kilohertz, the amplifier gain starts to drop. Falling a loop again means that the closed loop output impedance will rise. This continues until the loop gain drops below unity, at which the point the amplifier is no longer participating. And the external world sees the full 1K ohm impedance, and impedance which increases with frequencies inductive barrier. Behavior. So if you load it with the wrong capacitor, this inductive looking output node is going to resonate. Figure 1, a circuit example, and B is the output impedance of the block, and the test part GWE gain bandwidth. Here we can see that the frequency increases. To illustrate what the inductive phenomenon looks like in action, figure 2A shows that the unloaded output impedance of our example circuit of figure 1 and figure 2B presents that the loaded response of the example block used as an unity gain follower of 3 different capacitor values. To understand figure 2, remember that LC circuits resonate that at the frequency where the inductive impedance equal to the capacitor impedance. ZL equals to ZC. The two impedances have opposite phase, of course, and it is that is what accounts for the cancellation of the series impedance or parallel impedance we know as resonance. All three traces in figure 2 show peaking, which corresponds to the ringing in the time domain response, but CAP2 is the worst. Here we can see the figure 2a, the output impedance of the unloaded example block in figure 1 compared to the three possible capacitor load impedances. B shows that the loaded response of the example block used as a non-inverting follower CAP capacitor. Inductive reasoning. CAP2 has the highest peaking because the block output is closest to the pure inductor around 300k hertz, which you can see this by observing that the slope of the output impedance is closer to 6 decibel by octave, where it intersects the CAP2 impedance curve. At that intersection points of CAP1 and CAP3, the impedance is increasing with the frequency, but at the lower rate than 6 decibel per octave, indicating that the block has inductor-like behavior but is not a pure inductor at these frequencies. Hence, the peaking of CAP1 and CAP3 is not as severe. The slope of the impedance magnitude is nice intuitive way to look at the inductiveness, but the impedance phase is much easier to read off a plot than a slope is. A pure inductor impedance has a phase angle of 90 degrees. The closer your output impedance gets to the 90 degrees, the more it will ring when the loaded with the appropriate capacitor. At 90 degrees exactly, you should sustain continuous oscillation. Figure 3 is a plot of the output impedance magnitude and phase for our example block, and sure enough the phase maximum at 300k hertz, which loaded amplifier peaking is worst. Here we can see the figure 3, the magnitude and the phase output impedance of the unloaded example in the figure 1. This is a graph between the frequency and impedance magnitude in ohms. The figure 3 is almost all you need. It tells you the frequency range over which is amplifier output will look inductive, and it tells you what frequencies have the worst ringing and how bad it will be. The only thing left to associate each frequency with the capacitor value will cause ringing at the frequency. Remember, ZL equals to ZC is the condition of resonance. However, if you want, then you can go a step further, since the impedance magnitude to capacitance conversion is simple expression. Why not plot it for the every step on your AC sweep? There is here is a shortcut plot the magnitude and the phase of the capacitance to impedance equation times the imaginary unit J by 2 or into pi into frequency into output impedance, where the output impedance is the complex output impedance of the unloaded block as a function of frequency. Using the gray test circuit in the figure 1, this would be just a V test, but sure your simulator is using complex numbers for this waveform. The magnitude of this expression is desired capacitor value, and the J adds a space shift so that the phase plots directly as phase margin. This is displayed in the figure 4. At this point, we separate the grandstands and the real showboats from the pragmatics. Using the ZY, XY plot features of your simulator, MATLAB or Excel can do this if your simulator can't. Plot the phase margin versus capacitor as shown in the figure B. Figure 4a, the solid line is a capacitor load and which causes the ringing ringing at any given frequency. The dashed line is a frequency is the phase margin associated with the ringing at the same frequency. The arrow show that the 100 pf load peak of farads load causes ringing at about 4 megahertz with phase margin of 22 degrees. B shows that the information of A consolidated in a single plot of the phase margin as a function of load capacitor. Conclusion. Okay, now that you have this fabulous crowd pleasing and promotion worthy of phase margin versus load capacitance, what if you intend to load falls within the danger zone and you really can't change the capacitance enough to fix it? The great feature of this analysis is that it points you toward some concrete ways to improve stability. Since the inductive behavior depends on the circuit impedances and the falling loop again, here's what you can try: reduce a loop gain and reduced loop gain is this helps in two ways. First, recall the frequency range between open loop roll off and unity gain causes inductance. If you reduce the open loop gain, you reduce the dangerous frequency range, and hence you can reduce the range of problematic capacitors. Second, the worst case phase margin as approaches zero, and in the middle of the inductive range, if the range is narrow and that is the loop gain is low and the phase margin doesn't get very close to zero but it turns around, this makes the worst case phase margin somewhat better. Practically though, you are unlikely to have much flexibility here. Nobody has too much loop gain these days, and it is rare to have any that you can tradition. And also keep in mind that the loop gain can be limited by things like transistor output impedance, which may not be well modeled and can't be too aggressive. Change in the intrinsic output impedance of the block is equivalent to the changing root in the frequency figure 1. You notice that this change shifts of the amplifier output impedance curve up or down in the impedance, and this alters which capacitors intersect the most inductive region. Use zeros and poles in the feedback loop or load to address specific problem frequencies. The problems with this kind of ringing can be hard to fix. However, at least within the analysis, you can see what the options are, and the alternative is failing around blindly trying to tamp down some mysterious instability that you don't really understand. Thank you.